Okay, everybody, welcome back. So the work we've been doing with logarithms, it really is a lot of the point of it is to solve equations, and you're going to see that we solve equations involving logs, but also solve equations involving exponents. And solving equations, there's actually two ideas that we're going to be using here, which are as follows. If we have something to the x equals the same something to the y, it's very nice if we get this because we know that x must be equal to y. So this gives us x equal y. So somehow, if we're working in an equation and we can get an exponent with the same base on each side, so that this entire left side is something to a power and the entire right side is that same something to a power, then the powers must be equal. That's what this is saying. And a similar principle works for logs. If we have a log in base b of x is equal to a log in that same base b of y, this gives us that x must equal y. So if we can get our equation down to the form log equal log, where they have the same base, then we can get rid of the logs and we just set the things inside equal. The x must equal the y. And both of these we're gonna use them to make more complicated equations turn into simpler equations. More complicated log equation turn into a simpler equation. So that's going to be some part of our strategy. So these are the basic principles. Let's take a look at the first problem. A, 2 to the x plus 7 equals 32. Well, there's different ways to attack this, and we could certainly take the log of both sides, but we're actually going to do something different here. And it's only because I happen to notice that this 32 is related to the number 2. It's 2 times 2 times 2 times 2 times 2. Let me see, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. It's 2 to the power 5 gives us 32. And I just happen to recognize that as a power of 2. So 2 to the x plus 7 is equal to 2 to the power 5. And what we have now is, by rewriting the right-hand side in this way, this has allowed us to kind of shortcut to the end, because we have 2 to a power equals 2 to a power. And so what is it? X plus 7 must be equal to 5. The exponents must be equal. So x plus 7 is equal to 5. And now we can solve this by subtracting 7 on both sides, and we get that x is equal to negative 2. So in part A, answer negative 2. And we did that by getting the equation into the form something to the x equal the same something to the y. And then getting rid of the bases and just setting the exponents equal. Okay. I encourage you to pause and give the next problem a try and try to use the same idea for the next problem. For part B, we have 10 to the 2x minus 8 is equal to 0.01. And it's maybe worth noting that this 0.01, that thing is equal to 1 over 100. That equals 0.01. And 1 over 100 is, it's 1 over 10 squared. And 1 over 10 squared, we can move the 10 squared from the bottom up to the top and make the exponent negative. So this is equal to 10 to the power minus 2. And a good way to think of that when you're dealing with powers of 10 is if you have a decimal, you only have to think about how far to move the decimal over until it gets behind that 1. You move it 2 spaces over to get behind the 1, and so I know that it's going to be 10 to a negative 2 power. If we had to move the decimal 3 spaces over, it would be 10 to a negative 3 power. So I'm just going to rewrite the right-hand side. The left-hand side stays the same, and the right-hand side is 10 to the minus 2. And we can now apply the idea that says if we have the same base to a power equal that same base to another power, we can set the powers equal. So 2x minus 8 has got to equal negative 2 here. And then I can add 8 on both sides, and I get that 2x is equal to 6, and I divide by 3, and I get that x is equal to 2. So this is our solution for part B. Go ahead and work through part C, see what you can do with it, and we'll come back and do it. Here we go. So part C, 7 to the 2x minus 3 is equal to 7 to the 5x plus 4. Okay, this one is set up for you in a way that they want to try to trick you, but all you have to do is observe that it's a 7 to a power on both sides. And so we can use the same idea. 7 to a power equals 7 to a power. We can set the powers equal. This makes it seem like there will be something more complicated to be done here, but in fact there is not. And now we just have a simple equation. It's what we call a linear equation. It doesn't have any complicated x squareds or anything. What am I going to do? I'm going to move the 3 to the other side by adding 3. And I'm going to move the 5x to the left by subtracting 5x. You may have a different order in which you do these things in, and that's okay. The 3's cancel, and 2x minus 5x is negative 3x. The 5x's cancel, and the plus 5 and plus 3 is equal to 8. Now, if we divide both sides by that negative 3, we get that x is equal to negative 8 over 3. And I'll leave it as a fraction because that's the most exact answer. We could convert it to a decimal, but in a decimal you have to round it off eventually, and there you lose a little bit of the exactness of the number. So the answer here is x is equal to negative 8 over 3. Okay, let's take a look at part D. So this one, just grab it. Part D is 5 to the 3x plus 1 is equal to 25 to the 4x minus 7. Here they're making our lives a little bit trickier because we don't have the same base on both sides. However, I do make the following observation, which is that 25 can be written as 5 squared. So let's go ahead and replace the number 25 with 5 squared. On the left-hand side, 5 to the 3x plus 1 is equal to, on the right-hand side, that 25 is now 5 squared. And since the 25 used to be raised to this power, now the entire 5 squared is raised to this power, 4x minus 7. Now, we need to remember the rule of exponents, which says if you have something raised to a power and it's all raised to another power, you combine the powers by multiplying them. So we're going to multiply the 2 times 4x minus 7, and that's going to be in the new power of our 5 on that side. So left side stays the same, 5 to the power 3x plus 1. And on the right side, we have 5 to the power 2 times 4x minus 7. They're multiplied together. And I guess I'm going to do one more step here, which is just to distribute the 2 through there. So this is a 5 to the 3x plus 1 is equal to 5 to the power 8x minus 14. And this is nice because we now have the same base on both sides. 5 to a power equals 5 to a power. The powers must be equal. So we have 3x plus 1 is equal to 8x minus 14. Let me see. I'm going to subtract 3x on both sides to cancel the 3x off. And I'm going to add 14 on both sides to cancel the 14s. And we get 15 is equal to 8x minus 3x is 5x. If we divide both sides by 5, we get that x is equal to 3. Answer for part D, x is equal to 3. All right, go work on part E and come back. We'll do it together. Let's see. Part E, let's grab that one. Whoopsie. Oh, that's even better. Okay, this is E. Natural log of 3x minus 5 is equal to natural log of x minus 1. All right, so for this one, since they're a natural log of something equal a natural log of something, we're going to use the same principle, which is that if a natural log equals a natural log, then the things inside must be equal. So the 3x minus 5 must equal the x minus 1. Let's go ahead and solve this guy. I'm going to subtract x on both sides and add 5 on both sides. Let me see, 3x minus x is 2x. And on the right-hand side, minus 1 plus 5 is 4. And then we divide both sides by 2. And we get that x is equal to 2. Now, there's one more thing that we have to check here. We just have to be a little bit careful because we don't want, if we plug this number into the two sides of this, we don't want, when we plug this number in, to get a negative inside of a natural log, inside of any log, because a log of a negative is just undefined. Now, it's okay that there's a minus 5 in there because the natural log is of both the 3x minus the 5. So it's really a question of when you simplify the entire thing inside after plugging this in, do we get a negative? So let's just double check. The natural log of, I'm going to check by plugging in x equal 2 in for x in the equation and just see if it still remains equal. So 3 times 2 minus 5, and we want to know, is that equal to the natural log of 2 minus 1? Now, on the left-hand side, the 2 times the 3 is 6, so this is the natural log of 6 minus 5, and that's equal to the natural log of, if we simplify this, this is the natural log of 1. And natural log of 6 minus 5, that's natural log of 1, is equal to the natural log of 1. And we see that the thing that ended up inside our natural log, this guy is positive, so this thing is not a problem, and that verifies that this equation works. In fact, natural log of 1 is a value that we know. It may not seem like we know it, because what's the natural log of anything? But the natural log of 1 is always the same for any base. It's equal to 0. So this equation just turns into 0 equals 0. All right. Final answer, x equal 2. That's our solution for this one. Let's go take a look at part F. Hey, whoa. Okay. Part F. Let's take a look at this one. So here we have a log in base 2 is equal to a log in base 2, but it's not simply log equal log. This log has something added on the other side. And that means that we cannot simply drop the logs and set that things inside equal, because what about this plus 4 hanging around out here? So this leaves us with a little bit of a dilemma, a conundrum. And what we're going to do instead is we're going to move the logs together onto one side. So I'm just going to move this log over by subtracting it on both sides. So here we have minus log in base 2 of x plus 3 and minus log in base 2 of x plus 3. And so the left-hand side becomes the log in base 2 of x plus 5 minus the log in base 2 of x plus 3, and that's all equal to 4. Now, it hasn't gotten much better, but what we do have is on the left-hand side, we now have two logs. They're both log in base 2, and they're connected with subtraction. So we can combine these two logs together. And when we do that, we get log in base 2. When they're subtracted, we get a fraction inside, x plus 5 on the top, and x plus 3 on the bottom. And that's all equal to 4. Okay, we're getting closer. The thing that we have to remember now, because what we have is just log of something equal a number, in order to untangle this thing, one way that we can do it is by rearranging this log, rewriting it as an exponent. And if you remember how that rule went, so this is like recall, the log in base b of x equals y, that is the same as, well, we flip it around, we get b to a power. The power is the thing that's by itself in this one, the y, and the thing that's by itself in the new equation is this what was inside the log. So let's just, recalling that rule, let's apply that to our part f here. The base is going to be 2. The power is going to be the thing that's by itself over here, which is 4, so 2 to the power 4 is equal to, and the x, that's like the thing inside the log, it's the whole fraction in there. This is x plus 5 over x plus 3. Okay. Now, this equation, we need to solve it. Somehow, it no longer has any logs in it. It does have an exponent in it, but this exponent is just a number to the power of a number, so we can convert this into just a single number, 2 to the power 4. And that's 2 times 2 is 4 times 2 is 8 times 2 is 16. That's 16 on the left-hand side. So 2 to the 4 is 16, and that's equal to x plus 5 over x plus 3. Now, how do we get this thing solved for x? Well, the easiest way to do it is to cancel out the x plus 3 on the bottom. So I'm going to multiply both sides of this equation by the same thing. I'm going to multiply both sides by x plus 3. On the right-hand side, those cancel. So our right-hand side is just x plus 5. And on the left-hand side, I'm going to distribute my 16 through to each of these pieces. So I have 16x plus, and then 3 times 16, you might need to go and do a little bit of side work to find out. That thing is 48. So we now have 16x plus 48 equals x plus 5. What do I do now? I collect the x's on the left-hand side, so I subtract this x over here. That cancels that. And I subtract 48 on both sides as well. And that cancels that. So we have 16x minus x is 15x. And that's equal to 5 minus 48 is negative 43. So 15x equals negative 43. X is equal to negative 43 over 15. And this is our answer for x. Now, there is a final step, which is we should double check that we don't get a negative of a log when we plug this back in. I'm just going to observe negative 43. If we do 43 divided by 15, let me see, 15 goes into 43 2 point something times. And so you can imagine that's a negative 2 point something. If we put a negative 2 point something in here, we're going to add 5. That will make this positive. If we put a negative 2 point something in here, we're going to add 3. That will make this positive in here too. So we're not going to be given any trouble when we plug into this log. I encourage you to actually plug in and check on your own, and you'll see that that thing works out. Okay. That is the answer for part F. Let's go ahead and collect part G. Whee! Okay. So here's our part G. Log in base 6 of x equals log in base 6 of x plus 4, plus log in base 6 of x plus 4 is equal to log in base 6 of 5. Now, we have the same kind of log on both sides, but what we do not have is a single log equal a single log, and that's what we would need to be able to drop the logs altogether. So instead what we're going to do is we're going to combine things here, and hopefully that will allow us to drop those logs. So log in base 6 of x plus log in base 6 of x plus 4, since these are connected with a plus, we can combine them using the rule that says we get the log in base 6 of x times x plus 4. And on the right, that's the log in base 6 of 5. So what's nice about this is that since we have log in base 6 equal log in base 6, we can now drop those logs and set the insides equal to each other. This is x times x plus 4 is equal to 5. And now this one we can solve by first distributing the x. This is x squared plus 4x is equal to 5. I'm going to subtract 5 on both sides here, so we have x squared plus 4x minus 5 is equal to 0. This is a quadratic, and we could use the quadratic formula, but I think that we can factor it. Let's go ahead and give it a try. So we're looking for two numbers that multiply to give negative 5 and add up to positive 4. And those numbers are plus 5 and minus 1. So we have x plus 5 equals 0. That gives us that x is negative 5. And we have x minus 1 equals 0. That gives us that x is 1. Okay. We have two answers here, which is great, but we need to be careful that when we plug these answers back into our original equation, we don't end up taking the log of anything negative. So let's just check them. We're going to check first x equal negative 5, x equal negative 5. And if we plug that into our equation, we're going to have the log in base 6 of negative 5 plus the log in base 6 of negative 5 plus 4 is equal to ... I can tell already that this is going to be undefined because we can't take the log of a negative. So this is undefined. And that means that this solution, x equal negative 5, does not work. Now let's check the other one. Let's check x equal 1. So here we have the log in base 6 of 1 plus the log in base 6 of 1 plus 4 is equal to the log in base 6 of 5. So this is the log in base 6 of 1 plus the log in base 6 of 5 is equal to the log in base 6 of 5. Now, there's different ways that you can complete this from here. We could combine these together, and we would multiply the 1 times the 5 and get log in base 6 of 5 equals log in base 6 of 5. That would work. Another way to do it is just to notice that the log in base 6 of 1, the log of anything in any base of 1 is always 0. So this term is 0. And either way we do that, we get on the left-hand side the log in base 6 of 5, and on the right-hand side the log in base 6 of 5. So that means that our final answer for part G is just this guy, x equal 1. All right, one more to go. Let's take a look at H for this group. Here we go. Okay, guys, let's take a look at H here. For this one, well, we have a similar kind of setup, which is that we're going to need to combine two logs together. On the left, they're the same log in base 3, and they're connected with a plus, which means that we multiply the stuff inside. Now, we just have to be a little careful because the stuff inside is slightly more complicated. It's the log in base 3 of the first thing, x minus 2, times the second thing, x plus 6. And don't forget to put those each of those in parentheses. We need to FOIL out the stuff inside. So log in base 2 of this thing is equal to 2. I'm going to FOIL out. I'm going to simplify the stuff inside that log in base 3. So this is the log in base 3 of, if we FOIL this out, we get x squared minus 2x plus 6x minus 12. And that's equal to 2. And then in here, I'm going to combine the two like terms, the 2x and the 6x. So we have the log in base 3 of x squared plus 4x minus 12 is equal to 2. Now, we've gotten this equation in the form log equal something. And in order to untangle this, we're going to switch it around into an exponential equation. The exponential equation will have the base of 3 raised to the power, that's 2, and that's equal to whatever was inside here. So this is going to look like this. 3 to the power 2 is equal to x squared plus 4x minus 12. That's using the rule of rewriting a log equation as an exponential equation. Now, a little simplification here. The 3 squared becomes a 9. That's equal to x squared plus 4x minus 12. And let's see, if I subtract 9 on both sides, this is a quadratic, so I'm trying to get it so it's equal to 0. Those cancel, equal to 0. X squared plus 4x minus 12 minus 9 is minus 21. And then finally, we see if we can factor this thing. So this is x and x. We need two numbers that multiply to give negative 21, but add up to positive 4. And those numbers are positive 7 and minus 3. So splitting this up, this is going to give us two solutions. X plus 7 equals 0 says that x is negative 7. And x minus 3 equals 0 says that x is equal to 3. Those are our two solutions, and our last step, of course, is just to check those two solutions to make sure that they satisfy the original equation. So x equal negative 7, in particular, to make sure they don't give us any negatives inside the logs. So let's take this x equal negative 7 and substitute it in. This is going to be check x equal negative 7. So if we substitute it in, this is the log in base 3 of minus 7 minus 2 plus the log in base 3 of minus 7 plus 6 is equal to 2. And the left-hand one, log in base 3 of minus 9 plus log in base 3 of minus 1 equal to log in base 3 of minus 9 is not allowed because you can't take a log of a negative. And log in base 3 of minus 1 is also not allowed. You can't take a log of a negative. So this thing fails. And because of that, x equal minus 7 is not a solution. So let's now check the other one. This is the x equal 3. Check x equal 3. And for this one, let's see. The log in base 3 of 3 minus 2 plus the log in base 3 of 3 plus 6 is equal to 2. That's what we're checking. So this is a log in base 3 of 1 plus log in base 3 of 9 equal to 2. And in fact, the log in base 3 of 1, we know what that's equal to. That's equal to 0. And the log in base 3 of 9 is equal to 2. This you can check by changing it into a exponential equation, or you can just think through what it means to take the log of something. The log in base 3 of 9 is saying 3 raised to what power should give me 9? Well, 3 squared, and so that log is equal to 2. Now, if you were to rearrange this into an exponential equation, you would take the base 3 to the power 2, and that would be equal to 9, and you can see that that equation is also true. So we have a single solution here, and that solution is x equal 3. Okay, that's it for this set of examples. We'll do one more set of examples, and that'll be it for today.